we're going to start going in different directions. We've done the basic intersecting family knowledge from last time about intersecting, t-intersecting, whole world, or level, the R sets. In these next three, we're going to go in from different directions, all very interesting. And today we're going to look at covering by intersecting families. So the idea is this. We know how big an intersecting family can be, but now I want to cover the entire world with intersecting families. So I'll do some examples, and then I'll talk about it a bit, and I'll come to an interesting way of reformulation of it, which is basically why people would care about covering by intersecting families. So first question, how many intersecting families do we need to cover, well, I want to say the whole power set, but that's silly because the little dot called the empty set is in no intersecting family, so it can never be covered. So I'd better say minus the empty set. You know what I mean? I mean minus singleton empty set, you know what I mean, right? So the 2 to the n minus 1 sets that aren't the empty set. Okay, well, there's a stupid way to think about it and a sensible way. The stupid way would be to say intersecting families have size up to 2 to the n minus 1, as we know. We're trying to cover 2 to the n minus 1 sets, so maybe we can do it with 2 of them. But if you think about it, that's very stupid. If you look in the power set at the singletons, 1, 2, 3, and so on, I hope you agree that no 2 of those are the same intersecting family, right? So to cover intersecting families, you trivially need at least n. So need at least n, and you can also trivially achieve that. You take all sets containing 1, that's intersecting, all sets containing 2, that's everything. Everyone happy with that? So tick, answer equals n. Oh, just by the way, I'm talking about covering by intersecting families. If you said, no, I want to partition into intersecting families, it's the same thing, right? Because if you throw some stuff out of intersecting family, it's an intersecting family. So if I took my cube, if I covered it by, apart from the origin, these 4 intersecting families and their meeting, you just throw out what's in 2 of them, make it into 1 of them, right? An intersecting family with 5 sets removed is still an intersecting family. So I'll tend to say covering, it's the same as partitioning if you prefer. Okay, so far so boring. How about the level? How about the level? Let's try an example. Let's try... Oh, I've broken my... Oh, no. I've broken my own rules. So this does not mean the set 1, 1. This means the number 11. Can you manage to, just for a few minutes, pretend that this means the decimal number 11? Okay. So I want to cover the entire level. Now, if you think about it, you can find, in a world of 11, you can definitely find 3 disjoint 3 sets, can't you? Like 1, 2, 3, 4, 5, 6, 7, 8, 9. No 2 of those are in the same intersecting family, right? So certainly here you would need at least 3 intersecting families to cover. And in the general case, what we're saying is you can always find, I guess it's n over r integer part rounded down disjoint sets, right? Why can you find 3 and not 4? 3 sets in 11, because 11 over 3 is 3 and a bit, round down to 3. So you always need at least this. But you can do it better than that, because think about Erdos-Ko-Rado. Erdos-Ko-Rado tells you how big the world's biggest intersecting family is. It's 3/11, isn't it? So here, all intersecting families have size at most 3/11 of the entire world, right? Because remember, the biggest one is all triples from 11 that contains 1, and as we know, that's 3/11 of everything. So if each intersecting family covers at most 3/11, you need at least 11 over 3 intersecting families to cover. And that's about 3 and a bit, so you round up to 4. You can't do it in 3. So you actually need at least 4. And you would get an improvement, improves to n over r rounded up. So far, so good? So if we're doing triples from 11, trivial argument, you need 3 intersecting families to cover them. More grown-up argument by intersecting by Erdos-Ko-Rado, you need at least 4. And for general n and r, it would say you need n over. I'm just going to say n over r. I can't put it into parts. So what we know is we need at least n over r intersecting families. You're free to round up if you want to do rounding up. Okay, fine. But let's now actually find a construction. So let's now try and do it. Let's see how many we actually need. So to start off, you could pick a point like 1. Let's take all R sets containing 1. That's a good start, right? So start off with all R sets with element 1. Great. What should we do next? I guess what we see in front of us left is exactly all R sets from 2 up to n, right? So let's now take everything containing 2. You might call it the star at 2. So now go to number 2 and take all R sets with a 2. So now what you've got left to cover are the R sets living in 3 up to n. So you do it again. Now, okay, let's try this sensibly. You could be incredibly stupid and do this n times, but that's a bit silly because once you get to n minus r, there aren't any more R sets, right? There are no R sets that start with the number n minus 3 if r's more than 3. But actually, you can do better than that. So if you think about it, once you're down to the last 2r minus 1 points, they all meet, don't they? Oh yeah, I've got to say, sorry, as always, of course, we're assuming, as always, that r is less than n over 2. That's always our blanket convention, as always with EKR, right? Why is that our blanket convention? Because if r is bigger than half n, then the entire level is 1 in 6, so you do it in 1. And if r is half n, then you just say, to be an intersecting family, pick 1 from each pair. So if r is a half n, you'd say in each pair, put x in ax complement in b, that does it in 2, which of course is best. So we always have this convention. I won't say it again. So once we're down to the last 2n minus 1 points, that's one big intersecting family altogether. So you'd be going, the last one you do would be n minus, you would do the thing called n minus 2r, and having done that one, all the sets that remain start at n minus 2r plus 1 or less, right? So they all meet each other, because in terms of the world, we're saying, here is my dot, here's 1, here's n minus 2r, and if you live in the rest of the world, they will meet each other, because that's a world size 2r minus 1. So then you just add the rest. How many is that? That is n minus 2r plus 2. Right, because that's n minus 2r, and then you add one more. Okay, have I got that right? Have I got a number? I'm out by 1. I'm slightly worried. I think I'm out by 1, aren't I? Yeah, because the things that don't involve n minus 2r, there are 2r of them. Apologies, guys. So let's do a plus 1. And then that's even correct. Okay, so my Okay, so I do n minus 2r plus 1 of these kind of star things, these Erdos-Ko-Rado type A0 things, and then the rest as a kind of rump. Okay, right, but this number and this number are not so close to each other. I suppose, for example, that r was something like n over 3, a bit less or a bit more than n over 3, then this is roughly about the number 3. Maybe it's a 4 if I was slightly below, but it's 3 or 4, it's some small finite number. But this is a huge n over 3. So those are kind of absurdly far apart. So the question is, can you do better? Can you improve things, this construction? Or can you prove better bound? And this construction looks good at the beginning, right? Because we're using these fantastic, huge intersecting families. But at the end, it's kind of pitiful because they're not adding much in. Of course they're not adding much in, otherwise we get about n over r, and we're not getting n minus 2r. So they're saying going wrong. And the kind of remarkable fact is that this is the correct answer. That's what we're proving today. This one is the right answer. So it's kind of a very extraordinary thing. Even though intersecting families are absolutely huge, and think of it, R as about n over 3. Intersecting families can be fully a third of all sets, and yet you still need n over 3 of them to cover. So it's kind of an extraordinary thing, and that's what we're going to try and prove. This used to be called Kneser's conjecture. So it used to be Kneser's conjecture. But then, of course, Lovas proved it, so now it's called Lovas's theorem, of course. So that's what we'll be trying to be doing. But first, you might say, why do we care? And you could say it's quite a natural question, but why particularly would you care about covering by these things? So let me digress a bit and say why this is an interesting question. So at the moment, in the cube, we join two things if they're one apart, right? So on level R, okay, no two R sets are adjacent, of course, but distance 2 would mean you have two R sets meeting R minus 1 points. They're close. So that's the normal graph we've been looking at. The Kneser graph is kind of the exact opposite of that. So the Kneser graph, KNR, the vertices are, as always, the level. And you join sets if they're disjoint. So it's the opposite of the cube graph, right? In the cube, two R sets being disjoint means they're as far apart as they could possibly be. But here we're joining them. X joined to Y if X and Y are disjoint. Okay. As always, it's very hard to draw, of course. So if you had your ground sets being N, so here is an R set, here's an R set, here's an R set, then in the graph, this R set is joined to that one, this is joined to that, but they're not joined. I'm sorry for my rubbish, not a very exciting picture. When you do the examples, question 1 will ask you, draw one of those. Okay. So this is a very natural graph in combinatorics. It's the second most natural thing you can do after the cube. It's sort of a layer with this distance, and people are very interested in the question, what's the quadratic number of this graph? Again, I'll say in a moment why that's itself an interesting question, but for the moment, pretend you love quadratic numbers. And this is a weird, scary graph. So what says, remember, quadratic number means you've got to color it, And the rules are that adjacent things get different colors, right? That's what a coloring is. So in a coloring, this one and this one must have different colors. Now, what is a coloring in a graph? A coloring in a graph, here's a graph. A coloring means you assign to each vertex a color, and the rules are adjacent vertices are different colors. In other words, each color class is independent set, right? So you're literally partitioning into independent sets, meaning sets without edges. So maybe this is one of them. There's another one, and there's a third one, right? So coloring equals partition into independent sets. Now, what's an independent set in the Knaser graph? It's a collection of R sets where no two are joined. That is literally intersecting family, right? That's exactly the same statement. If I have a family of R sets with no two joined in the Knaser graph, that literally says I have a family of R sets where no two meet. Right. So that equals the least number of intersecting families to partition or cover, it doesn't matter, of course, to cover XR. And that's basically why people care about that covering question. It's because it's asking for the correct number of the Knaser graph. Now, why is that an interesting question? Okay, you could just say this is a very natural graph, I love it, but there are other reasons why it's interesting. One is going to be that in this graph, we're having quadratic number chi is very large, even though the independent sets can be huge. Again, think of, as before, think of R as being about n over 3, for example, right? Then this is saying the quadratic number chi is like n minus 2r plus 2, so like a third of n, but this thing here is r over n of the total, right? And of course, I mean times the total. So that's quite striking. Now, of course, in general, if someone said to you, please construct a graph with the biggest independent set big, but needing lots of colors, that's incredibly easy. I would take 10 to the 10 singleton points and insert over here in the corner a K1000. Okay, so I'm taking 10 to the 10 independent points and a K1000. I hope we agree there's an enormous independent set in this graph, right? Way over half the size. But obviously, you need at least 1,000 colors because of the K1000. Right, but that was stupid because not all points look the same in that, right? The independent sets don't look, not all, the interesting points are other types of points. The point about the Knaser graph is that all points look the same. I hope you agree that any R set equals any other R set. Right? The formal wording would be that given any two R sets, there's an isomorphism of the graph with itself, mapping this out R set. But it's obvious, right? It's permute the ground set. So the point is, and the Knaser graph is transitive. Transitive means all points look the same, right? And that's much harder to do. So again, this was a stupid thing. If I say to you, I want a graph where you need lots of colors, even though the independent sets are big, and all points look the same, that's a much harder thing. And another way of saying that, so suppose I took the Knaser graph and I just took the following intersecting families, everything with 1, everything with 2, everything with 3, and so on. So you can find you do have n independent sets with each point of the graph in R of them. Is that right? So I take, again, the star at 1, everything with a 1, everything with a 2, everything with a 3. That is n independent sets, and each point's in R of them. So you can kind of, it's not quite a colouring, it's a kind of colouring with sets of more colours. And if you know about fractional quadratic number, it turns out this says that the fractional chromatic number, well, it is actually n over R. Fractional quadratic number, if you haven't met it, it basically says you want to find some independent sets. You're allowed more than what you want. If you cover each point t times, you divide it by t, and that's your fractional quadratic number. And so, obviously, if you have any graph, you could just cover each point once by colouring. So fractional chi is always at most chi, but the question, can it be 1 less, is easy to do. Can it be 3 less, easy to do. If you want it much less, then this is basically the first example known. It's a fractional thing because basically all points look the same. That's what made that work. So the Canesa graph is interesting because basically it's a transitive graph. It's almost the simplest possible transitive graph in which, even though independent sets are enormous, say R is over 3, you just need lots to cover. So that's why it's very intriguing. Right, so this was open for many decades before Lovas solved it. And Lovas's proof used some algebraic topology, used a lot of very clever algebraic topology. I'm going to assume you know 0 algebraic topology. If you know some, then humble apologies. So it turned out that after Lovas, let me do some history here. Used, I'll say lots of algtop. Very, very clever, subtle homology stuff in complexes, very, very clever, very wonderful. And then, just a few months later, and actually published in the same edition of the same journal, but that was deliberate, Baragny found a much shorter proof using only the Borsuk-Ulam theorem, which I'll tell you about in a moment. I assume you haven't met it. So it's one of the standard algtop theorems. So he used Borsuk-Ulam, which I'll tell you about in a minute, plus some other stuff called Gale's theorem, which is about, roughly speaking, you have some high-dimensional sphere, you want to put some points on it so that no direction is biased somehow. So it went from being a very long proof to a kind of 3-page proof, so much shorter, and everyone said, this is, how amazing, this is obviously the proof from the book. This is obviously the ultimate proof of Case's conjecture, how wonderful. And then matter stood, and then Joshua Green, some years later, managed to find a proof just by Borsuk-Ulam, an even shorter proof. So it's kind of clear that Green's proof can't exist. It's kind of, when you read Baragny's proof, it's obviously the optimal possible proof of this. You have Borsuk-Ulam, there's some other stuff with putting points on a sphere, and it's tailor-made to make it work. And then, as we'll see, Green put a tiny twist into Borsuk-Ulam and made everything work out fine. So that's what we're going to do. I'll talk a lot about a theorem called Borsuk-Ulam. I'm not going to prove it, but I'll talk about it, give some equivalent forms of it. If you want to see a proof of Borsuk-Ulam, you either have to go to an algebraic topology book and learn some homology, or there is a combinatorial proof as well. So some books will have a proof, or so online you can find notes which do prove it combinatorial, but it's pretty hard to prove. So I'm not going to prove Borsuk-Ulam. It's either a big piece of combinatorial work, or you have to understand the scarier of the two H words. You have to understand not just homotopy, but homology. So it's scary stuff, so I'm not going to do it here. Okay, so let me tell you about Borsuk-Ulam. So I'm going to normally write Sn for the unit sphere in n plus 1 dimensions. So for example, this is S1. It's just a circle, okay? Officially, it lives in R squared, as I've drawn it, right? It's called S1 because it's kind of a one-dimensional object. That's why it's called S1, not S2. How about S2? S2 looks like the surface of the Earth, right? Not solid ball. I don't mean the unit ball. I don't mean everything inside it, just the surface. Is everyone happy with that? So everything at distance 1. So there's an S2. Okay. Of course, I can't draw you an S3 because I can't draw four-dimensionally. Hope you get the idea. Okay. And what Borsuk says, if you have a continuous function which goes from Sn down into one dimension, down into R to the n, then there are two opposite points taking the same value. Then f of x is f of minus x for some x. So let's think what this is saying. Let's start off with S1 and then go to S2 to get a feel for what Borsuk is saying. So in S1, it's say you have some, here's S1. You have some nice f just going to the reals. There should be two opposite points taking the same value. Making sense? So you should be able to find somewhere two opposite points, x and minus x, where the function's the same. Why is that true? Well, that's actually quite easy to see if you imagine moving points around. Because suppose it isn't true. Suppose that actually, well, okay, let's just start saying pick your favorite opposite pair. So pick an x and a minus x. Okay. If they're equal, we're done, we go home, we're happy. If they're not equal, let's say that f of x is bigger than f of minus x, let's say. And now I want to say, I'll call this point x0, let's say. Now I want to imagine what happens as you rotate x0 around. So think about the difference. I'll say the function g of x defined as f of x, take away f of minus x. Okay? So the difference is, if it's 0, we're done. We want it to be 0 sometime. Now at x0, we know that g of x0 is definitely positive, right? Because that's what we said. It's bigger than f bigger there than there. But once you get to minus x, it's negative, right? Because if you do g of minus x0, then at that point, it's this that's negative. So by intermediate value theorem, just in the normal for a real interval, I've got a function of x, which is pos here, neg here. As you waddle it, let's go through 0, because everything's continuous. So IVT implies g of x is 0 for some x. Okay, so that was basically easy. So Borsuk for S1 is just intermediate value theorem. That's the end of the story, I'm afraid. I can't do the same for you for S2. I can say what it says for S2. It says you're mapping to R squared. For example, maybe you're taking at each point the temperature and atmospheric pressure. Then Borsuk would say, whatever the distribution of temperature and pressure in the world, there are always two opposite points where they're both equal. Oh, this is another physics interlude. Fantastic, I'll write that down. So there exists x and minus x, antipodal point, with the same temperature and pressure. Again, if you try some examples, like you take a map of the globe and you look at the temperature pressure, you'll find it's true. But there's no argument that just says it's essentially intermediate value theorem. In fact, many people call Borsuk-Ulam, they call it the higher dimensional intermediate value theorem. Because obviously something to do with that somehow. And actually, this trick of looking at f minus another point is going to come in a few times as well. So this was a useful thing to be doing. Let me also convince you that, so I'm just going to chat a lot about Borsuk-Ulam, and after the chat, it'll take us less than 10 minutes to prove Knase's thing, but I'm just going to basically chat. So here's why Borsuk-Ulam cannot be an easy theorem to prove. Here's why there cannot be a thing where you say, think a bit, apply a cool IVT, apply induction, we're done. Here's why. Suppose you know Borsuk-Ulam. Okay. Then I hope you agree that certainly tells you that if you map from Sn to Rn, you're not an injection, right? There are some 2 points with the same value. And the opposite point implies no injection from Sn to Rn. Fine. It says much more than that, of course. Now, Sn, remember, that lives in R to the n plus 1. So that tells you, of course, I mean continuous. Everything will always be continuous, but I probably ought to write it. Sorry, folks, I ought to write it. But I'll probably stop writing. Everything's always going to be continuous. Now, what does that imply? It implies that certainly these two spaces are not homeomorphic. Right? If these were the same space, if r to the 4 and r cubed were the same space, by checking these both ways, then trivially, any subset of r to the 4 would inject into r cubed by the homeomorphism. So this already implies that r to the n plus 1 and r to the n are not homeomorphic, not the same space. And that's sometimes called Brouwer's invariance of domain theorem. And it's pretty hard, as you might guess. I mean, obviously, r versus r squared is easy, because if I gave you r and r squared, you could say, well, in r, remove a point, you disconnect it. And that's definitely false here. So those aren't the same. Great. Let's do r squared versus r cubed. Well, I guess if you remove a point of r squared, there is a loop you can't contract, right? But if you remove a point of r cubed, every loop you can contract. So they're different. R cubed versus r 4 is pretty hard. You'd like to say, oh, there's a higher dimensional sphere you can't contract, but why can't you contract it? So if you don't believe me that this is a hard theorem, try and prove it for, say, r to the 4 and r cubed. So I'll say, e.g., r to the 4 versus r cubed. And that's really, really, really hard. So that's basically why Borsuk-Ulam cannot be easy, because if it was, you'd trivially have proved that, and hope you can believe that's going to be a hard thing to prove. Oh, there are other forms of this theorem, by the way. This is one of the 2 or 3 theorems called invariance of domain. Okay, so let me show you some other forms of Brouwer, which are quite nice. Sorry, Borsuk-Ulam, sorry. So the mapping G we had before, wherever it's gone, never mind, had the nice property, remember, that G at a point was minus G at the opposite point. That's called an antipodal map. So definitionally, in general, that G from Sn to somewhere, some r to the n, could be n plus whatever it is called antipodal. If g of minus x is minus g of x for every x, like the example we had over there. So Borsuk-Ulam is equivalent to the following assertion. It says, if you want to map from S2 to S1, well, there's plenty of continuous maps that do that, but you can't have an antipodal map. It says you can't have a map from S2 to S1 that preserves oppositeness, and same in general. If and only if there is no antipodal map from Sn to Sn minus 1. That's what I'll try and say now. Oh, what do I mean by equivalent? And of course, if you already know they're both true statements, you know they're equivalent, you can take what I mean here to either mean it's easier to prove that they're equivalent without proving the whole of Borsuk-Ulam directly, or you can take as meaning I'm going to prove they're equivalent. So that's officially what I mean by this. I don't just mean they're both true statements, which they are. I mean I'm going to prove they're equivalent. Okay. So why is this the case? Well, suppose you know Borsuk-Ulam. So suppose I know Borsuk-Ulam. Now, given an antipodal G, and of course everything's continuous, I'm not even going to say it, G from Sn to R to the n, right, which is more general than that even, we know it's equal to opposite points, right? Because, yes?
That's a silly question. Why can't I just map everything to 0?
Because 0 is not in Sn minus 1.
Yeah, but just pick a point and I map everything to a single point.
You can do that, but then opposite points all go to that one point, not to its negative. Okay, right. So yeah, so S2 to S1, mapping to one point, nothing maps to the opposite point, so it's not an antipodal map.
So this works going to S0. If there were such a
Yes. Depends whether you, well, maybe S0 is all points in R to the 1 at distance, probably it's a 2-point set. So so I think it's not even true for S0, but yeah, okay. So if there were G from S, now by Borsuk-Ulam, every function, antipodal or not, there's a place where f of x is f of minus x. So we would get g of x is minus g of minus x for some x. Sorry, g of x equals g of minus x, but you're antipodal, right? So g of x equals minus g of minus x. So if you have a point in R to the n, which equals its negative, it's 0. So that would imply, so g of x would be 0. In particular, you're not on the sphere, right? So I'm saying if you take Borsuk-Ulam and you apply it, it says for your function, any old function g, at some to opposite places you take the same value. But if you're antipodal, at those places you take opposite values. So the value v you take has the property that at these 2 points, the values are v and v, and they're also v and minus v. Therefore, v is 0. Making sense? And v isn't 0 because I map to the sphere, not just R to the n. So that's one way round. The other way is actually equally easy. So suppose Borsuk-Ulam is false. I've got to find you a cool antipodal map here, right? So suppose Borsuk-Ulam is false. So we have our nice f from Sn to Rn with f of x never f of minus x. Okay. Now, we want an antipodal map to do something like that, so we literally just apply what we did before in the one-dimensional case. We take the exciting function f, take away f at the negative place. Right? So define g, also from Sn to R to the n, given by x maps to f of x, take away f of minus x. That is antipodal, right? Because at x, it's fx minus f of minus x, but at minus x, it's f of minus x times f of x. They're opposite. So this is antipodal. Now, where does it map to? It doesn't hit 0, does it? So it maps to r to the n minus the origin, but then you just project out to the sphere. Is that making sense? Right? Like if I gave you, for example, a function to the plane that was never 0, you just project out to norm 1. Right? You make it map to S1. So if I map to here, I make it go to there instead. Map to there, I go out to there. Right? I don't want to write out. Officially, I'm saying take the new function g of x divided by the length of g of x. But it's always continuous because you didn't go through 0. Okay, so that's actually quite a nice equivalent form of Borsuk-Ulam, this thing over here. Okay, so let's kind of remember that. Okay, now comes the kind of the reason why Borsuk-Ulam has combinatorial applications, and in general, the following is how Borsuk-Ulam tends to be used most of the time inside topological things. So here's S1. I want to break it into sets where no set has two opposite points. Does it make sense? So I want to cover, or partition, doesn't really matter, S1 into sets where no set has two opposite points. Well, that's trivial. For each opposite pair of points, put one in A, one in B, you're done. But those are very weird, ugly sets. I could take, for example, this point and the semicircle, but not including that point, and then the rest. Everyone happy with that? So if I took that set and then this set, so by a dot I mean it's in, by a circle I mean it's not in. I've covered by two sets, but those aren't closed sets. They're not nice sets. I want closed sets. So I want to cover Sn by closed. Closed meaning limits of the set are in the set. Closed sets, none containing an antipodal pair. If you think about it, you just can't do it in S1. If you try and do it, because you have to have the endpoint, you just kind of always die. You'd have to have this endpoint in it, and then those would be those would be opposite, not allowed. If you try and do separate intervals, you find it goes wrong again. You just find it can't be done in 2. It can be done in 3, of course, very easily, right? You can do it in 3. You just take your circle, just cover it with 3 arcs of a circle, all of length less than 180. Make sense? So by 180, I mean pi, whatever it is. So here's one, here's another, here's a third. So S1 you can do in 3, and it turns out you can't do it in 2. Now how about S2? It turns out this you can't do in 3, actually. Here's some intuition. What would be an obvious, really, really big set to take with no antipodal pair? It would be like a hemisphere, but stopping just before the middle, right? So you could take everything, say, above epsilon above the equator here. That's your first set. That looks good. But notice what's left is a copy of S1 and other stuff as well. We know from our earlier work S1 needs at least 3, therefore at least 4. Of course, that's not a proof, because your first set might look like that, but I hope you give some intuition. So what seems to be the case is that it seems that you can't do it in n plus 1, but you certainly, it's a question mark, you certainly can always do it in n plus 2. Right? Here's an easy way to see that in general. So why can you always cover with n plus 2? So I'll first take so I'm trying to do S2 in 4 sets, right? I'll first take the upper hemisphere at epsilon, then the right one, then the front one. So I'll take the set of all x in the sphere whose first coordinate is at least some tiny epsilon. Then I'll take all the x with x2 at least epsilon, dot, 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 all the x with xn plus 1 at least epsilon. Now what's left to cover? It's points which have all coordinates or negative or positive less than epsilon, right? So the remainder, the sort of the rump, the remainder is covered by the set of all x such that xi is at most epsilon for every I. Make sense? But if you think about it, that has no antipodal pair, right? You can't have a point with all coordinates less than epsilon and more than minus epsilon, as long as epsilon's bigger than 1, less than 1 over n or something. That makes sense to everyone? There's no point in S2, all of whose coordinates, all 3 of them, are less than 1 over 100 and more than minus 1 over 100, right? Because that wouldn't have length 1. So in general, you can always say, remember, Sn lives in after n plus 1, remember? You take the n plus 1 hyper half spaces brought in slightly, and what remains also doesn't have a typical pair. Okay, good. So we can always do n plus 2, and it appears you can't do n plus 1, and that's going to be an important thing for us, so I'll talk about that now. That's called the Lussinic-Schnirelmann theorem. And it says, if you write Sn as a1 up to a n plus 1, brackets each closed, then some ai contains an antipodal pair. Okay, which is what we're trying to prove. There are a vast number of spellings of this pair of names because there are a vast number of ways of spelling this and of spelling that. I think there are at least 4 ways of spelling the literature. Also, I'll warn you, if you Google this name, you may find this theorem or a different theorem, which is called the Lussinic-Schnirelmann category, which is also about Alge-Top, but it's totally different. So make sure you find the right theorem. Okay, and this is going to be very useful to us. I'll say why it's true. I'll deduce it from Borsuk. It turns out, actually, it's equivalent to Borsuk. I'm not going to prove that here. It turns out it's quite easy to see that if Borsuk-Ulam was false, this would be false as well. But that isn't interesting for us. All I care about is this is a true theorem. So let me prove it to you now. It's a very, very elegant proof. And then I'm going to come back and modify this in the way that Green modified it. So I'm going to modify that in a moment. It's actually a very simple proof. What we do is we define a map F from Sn to Rn by, for each point, you ask how far is it from each set. Right? Are we all happy that in general if I have a point and a set, that distance means the inf of the distances? Okay. Distances are retained because the sets are closed, so they're compact and so on. So let me map, given a point x, I'll map it to the following entiple, the distance from x to a1, dot, 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 the distance from x to an. You should be slightly worried that there were n plus 1 sets. We've dropped one of the sets, but it's going to be okay. Right? Do we agree this is a continuous function from Sn to R to the n? Continuous, if you move a point by a tiny amount, the distance doesn't change by a tiny amount to anything. It changes by very, very little. Okay, so what do we know? We know that there is some x by Borsuk-Ulam where x and minus x take the exact same value, right? So there exists an x such that the distance from x to ai is the distance from minus x to ai, not for all I, but for all 1 at most I and most n. Making sense? That's what Borsuk tells us. Now, where are the points x and minus x? They've got to be, each one's got to be somewhere, right? Remember, our dream is to find an A that contains both of them, because that's what we want to prove, right? If both x and minus x are in an plus 1, then we're done, right? Because, oh, look, there's an antipodal pair in an plus 1. So we can assume that doesn't happen. So at least one of x and minus x belongs to one of a1 to an. So if I simply just say log, by replacing x minus x, let's say x belongs to a1. Right? Remember, x has to belong to one of the a, so does minus x. They don't both belong to n plus 1, so one of them belongs to one of the a. Say x belongs to a1. Right, what does that tell you? That tells you, rather trivially, that the distance from x to a1 is 0, because you're in the set, right? Therefore, the distance from minus x to a1 is also 0. But you're a closed set, right? So if the distance is 0, that means you're in the set, right? Because the set contains its boundary. So minus x actually belongs to a1. And we're done. Quite painless, right? Quite nice. Okay, let me now show you. So Baranier's amazing proof said, take Borsuk-Ulam, written, of course, in the Lustig-Schnirel form, and do some cool stuff. So let me tell you Joshua Green's twist on Lustig-Schnirelman. So when you see it, it looks like you're going to think, why would anyone ever write down such a thing? So remember, we know that if I don't insist their sets are closed, if there's no condition, you just do it in 2 sets, right? For each x, you put x into x complement to b. Green says, suppose I partitioned into sets, and each one is either closed or open. Then we're done. We're not saying they're either all closed or all open. We're just saying each area is either closed or open. So each closed, so I'll put my change in orange, or open. Same conclusion. Right? Looks like a just perverse, ridiculous thing, but as we're going to see, it's going to be pretty useful to us. Okay, let's try and prove it. All right, so again, I've covered it with sets. Each one's either closed or open, and we want to show this in pair one. So off we go. Exact same function. Again, slight sick feeling. We didn't mention n plus 1, but we live with that. Again, there is an x where they're equal at all those distances are all equal. Remember, of course, if you're an open set, distance 0 doesn't mean you're in the set, you're on the boundary of the set, right? But let's carry on. If they both belong to n plus 1, then we're done, as before. Therefore, one of x and minus x belongs to at least one of a1 up to an. We'll log its x itself by swapping x and minus x, we'll log its a1. So we'll log x belongs to a1. Fair enough? Same so far. Okay, then we say, if a1 is closed, we do what we did before. Fair enough? What if it's open? All right. So what do we know? Let me draw something. So here is x, and way over here, at the opposite place in the sphere, is minus x. Now, what do we know? X is in A1. A1 is open, right? So there's a little disk around X, which is totally contained in A1, right? That's what open means. Fair enough? Now, how about minus X? Well, the distance from minus X to A1 is 0. That doesn't mean X is in A minus X is in A1, but it means there are points in A1 arbitrarily close to X, right? So I can find you an incredibly close point, much less than this distance here, which belongs to A1. Oh, but now we're done. This point works, right? because this point's in A1, and so is its little minus over there. So we're done. So it's quite cool. It's not true for general sets. It's true if they're all closed. It's true that each one's either open or closed. So it's quite bizarrely nice. Okay. Now let's use this to now prove Knaser's conjecture. So let's now prove Knaser. Let's suppose, for a contradiction, that we've covered x brackets r with, remember, we're going for n minus 2r plus 2 with, let's say, n minus 2r plus 1 intersecting families. I'll call this number d, okay? So d is one less than what I think the answer is. So we're trying to rec d. Let me call those C1 up to CD. Okay, now, let me consider SD living in R to the d plus 1. I'm going to think of my n-point ground set as being n points on this sphere. Okay, so here's 1, here's 2, here's 3, here's 4. So I'm identifying x with n points in Sn, in SD. I want them in general position, meaning you pick them at random, no coincidences. Let's just think what general position should mean. Supposing I was in S1 for a second. Here's the special point called the origin. Of course, any 2 points determine a line, right? I would want that line not to go through the origin. That's what general position means, okay? That you take any 2 points in your set, you join them up, it doesn't go through the origin. Making sense? In S2, what does general position mean? Again, we have an origin somewhere, not in the S2, of course. Now, any 3 points determine a plane, don't they? The rule will be it mustn't go through the origin. Okay? So, any 3 points in your set, they're planes through the origin. So the rule is going to be, general position is going to mean no hyperplane through the origin has d plus 1 points. Making sense? So in S1, it said take a line through the origin, doesn't have 2 points in it. In S2, take a plane through the origin, doesn't have 3 points on it, and so on. Making sense? Of course that exists, right? Just pick your points at random, or if you prefer, pick your endpoints, and if you're unlucky, you perturb 1 by epsilon to stop one plane happening and do it repeatedly. So it certainly exists. Okay. What are we going to do with that? We're going to try and write down some cool open or closed sets. Now what are we going to do? Here's how I'm going to define some sets. So here's my sphere. Here's a point x. Think about x's half space. Think about the stuff which is in the upper half of x. Now, some points of our set, maybe none are in there, maybe they're all in there, who knows, are the n points. If r of the points are in there, I would say, whatever color whichever of the families that's in, that's where I put x. So my rule is going to be, let me write it down carefully, I'll define A1 as follows. It's all the x with the following property, the half space of x, right? That means the hemisphere, open hemisphere centered at x, has r points which happen to be in the class, in the intersecting family C1. Is that making sense? Of course, x could be in many, many sets, right? If in this half space I've got an R set that was in C1 and R set in C2, then x is A1 but in A2. Is that making sense? So A1 relates to the intersecting family C1. A1 says It's all the points whose hemisphere contains some R set, which was an intersecting family member C1. Is that making sense? All right. Oh, that is, of course, open, isn't it? Because it was an open half space, right? If I have an actual R set in it, in C1, that's a finite distance from the boundary, so if I move X slightly, it stays in there. So that's open. Good. A2, same, for 2. Dot, 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 an plus 1, the same. Making sense? And finally, an plus 2 is the rest. Now, what is the rest? How could you have a point that gets, let's say, none of the A's? That would mean no R set in it is an intersecting family. That means it's less than R points. Everyone agree with that? If it's got R points in the hemisphere, they're in some CI, maybe several, so we're done. So, rest equals the half space of X has at most R minus 1 points. All good so far? Yes. D, thank you. Apologies. A D plus what? Wait. There are D of these things, so it's AD, thank you, AD plus 1, because we're in SD, apologies, we're in SD. Thank you. Okay, we're less than 60 seconds away from finishing. So what do we now say? By Green's version of Borsuk-Ulam, one of these, at least, has an antipodal pair. Now, there's no way it's A1. How could A1 have an antipodal pair? That would mean you have two opposite points, in each of whose half spaces you had R points in intersecting family C1. That's just false, right? Because R points upstairs and R points downstairs are disjoint. Right? Because the exciting fact that the open half space at X and minus X don't meet. Make sense to everyone? So there's absolutely no way it could be A1. Because if it was, then the intersecting family C1 would have an R set up and R set down, which don't meet contradiction. Okay, so it must be in the rump part of the world, you have an opposite thing. So you must have an X and a minus X with the following property, that in the half space of X, you have at most R minus 1 points, and in the half space down here, you have at most R minus 1 points. Oh, but how many points are in the middle hyperplane then? So the middle hyperplane has at least, what does it have? There were n points initially. I removed R minus 1 twice, but that is, sadly, at least D plus 1. Right, because D is n minus 12 plus 1, and that's a contradiction to general position. Because remember, general position said no hyperplane through the origin, no great circle if you like, has D plus 1 points in it. So we're done. So it's really kind of amazing. What it's saying is that somehow these weird, very subtle properties of the sphere are telling you what's happening inside the level, inside the Canesa graph. And final thing to say is that very often, if you're doing some graph theory stuff, and you have something which seems to be true, but might not be true, and it's got to do with things about being large and being small, and something of the form, I have a lot of these big things, so should I can cover that with them, you should always try it out on the Canesa graph. So there are lots of things in maths where the answer is it's false because of the Canesa graph. One example I mentioned was fractional chi and chi, but there are many others. Right, so we'll stop there. That's the end of our proof of Canesa conjecture.